Welcome to the HMD Contro GSPV Upgrade and Replacement Webinar. My name is Anna Mizell, and I'm the Sundyne ASM for the oil and gas team down in Louisiana. Our presenter today is Charlie St. Laurence, who's a business development manager at HMD Contro, and he presented some of the content from our webinar series last, I think it was April. So Charlie, take it away.
Yeah, thanks very much, Anna. Welcome everybody, and thanks for joining the webinar. So today we will be discussing the GSPV Upgrade and Replacement Initiative. So just to start, I mean, we had a fantastic response to the webinar we held last year for the A01S. With that in mind, we have looked to apply a very similar approach to the GSPV. There is a lot in common with the A01S strategy that we can use in the same way. We want to present this as an upgrade and replacement opportunity with seal-to-seal-less benefits. I know that some of you will be more familiar than others with API 685. So I wanted to start the show with this slide, just to remind everyone how long this specification for seal-less pumps has been around. 20 years, it's a long time. It means this specification has good history behind it now, which means it has built some good experience. It's not a new specification anymore. It's about to enter its third revision, so it's been updated, it's been improved. And as you can see from the top line there, HMD, they've represented on the subcommittee since the first edition in 2000. So this is not just a specification that we design our pumps to, but it's one that we've played an active role in producing. And as you can see there, the third edition was actually due for release in 2020. This has been delayed due to the pandemic, but it is due. It is due soon. So just diving into the technical now. So firstly, I'll highlight the difference between the GSPV and the 801S, because I do get asked this quite a lot. The 801S is a Sundyne LMV 801 hydraulic end with an open type basket impeller and a cone-shaped diffuser with an HMD mag drive back end. And that design, that offers optimum efficiency for those low flow, high head applications, where on a traditional impeller, that would sit sort of far left of the curve and not be particularly efficient. So the GSPV, this is purely an HMD design, and this is utilising a closed impeller, but it's also using a diffuser. But in the GSPV, it's a radial diffuser, and that you can see in the centre of the screen, and also in the top right. So using the diffuser in this way, this means that we can offer high and low flow versions, which increases our range and therefore our ability to fit the duty to the curve. The pump, it's API 685 compliant, it's rated to 40 bar, but this has a maximum temperature of 205 degrees, which is a bit lower than our horizontal pumps, and this limitation is due to the heat rising into the motor. And the motor, by the way, and the motor that is required is a standard motor with a seat face mounting. Dimensionally, it's compliant to BS 4082 dimensions, class R. There is some interchangeability with competitor units, but only on those that are designed to the same BS 4082 class R dimensions. We will look at this in a bit more detail later. So in all of our vertical pumps, we've swapped the thrust bearing material for the harder wearing CMC material. This is just to mitigate a situation during startup where the customer may not have vented the pump correctly, and there may be a brief moment of contact between the bearings, before any trapped air is then pushed through. This CMC material, this will prevent any damage, and it makes the pump more robust, prolonging its life. But we haven't, we've never had any startup issues relating to this. But it also, if you do get an upset condition where, a bit of cavitation, where you do, again, it will help in that condition as well. So if you do get that brief contact. The GSPV, it's also compatible with the Vapor View and the Zero Loss Shell, which we're going to look in a bit more detail now. But just one quick slide before that. Here is the coverage of those 9 hydraulics at both 50 and 60 hertz, 4-pole and 2-pole speeds. You can see it does offer a really excellent sort of coverage. You know, we can get down to a reasonably low flow there at around 20 to 22 gallons a minute, and we can get all the way up to around 1,000 gallons per minute. Now, I'm sure that most of you are familiar with our zero loss shell. For those of you who are unfamiliar, the zero loss shell, it eliminates the coupling loss that you get with a metallic containment shell, which means there's no heat is getting passed back into the liquid. It's lower absorb power, meaning smaller motors can be used, higher efficiency, and also the opportunity to develop larger magnetic drives because we don't have to compensate for that power that's getting lost with a metallic shell. So the zero loss shell plays a key role really in the upgrade and replacement program in many ways. So this slide, this shows the benefits of the zero loss and also the pressure temperature profile comparison between a traditional metallic containment shell versus a zero loss shell. So with a traditional metallic shell, you get magnetic coupling loss between the inner and the outer magnet ring. And this lost power, it manifests itself as a heat that is transferred into the liquid. So when pumping volatile liquids such as hydrocarbons, this will raise the temperature of the liquid, moving it closer to its vapor pressure. Now, and this effect, this can be seen on the graph at the bottom there on the left-hand side with the orange profile, and that is called a pressure temperature profile. The blue line, this shows our liquid vapor pressure, and the orange line there, that tracks the temperature of the liquid as it enters the pump suction, and it's then recirculated through the back of the pump to cool the coupling and lubricate the bearings, which, as we know, is crucial for the operation of a mag drive pump. So hopefully you can see my cursor there on the screen, but that beginning part of the profile, that's the liquid as it enters the pump suction. It then meets the discharge pressure, so it moves steeply away from the vapor pressure. And this part here at the top, where it comes back round, this is the liquid that's being recirculated around the back of the pump. And then this section of the profile here, where you can see it's losing pressure and picking up the most heat, that's where it's traveling along the surface of the inner magnet ring and picking up that heat. And then here at the end of the profile, that's when it returns to the high pressure area. Okay. However, if you take the same application and you compare that to the zero loss containment shell, the benefits become immediately obvious, and you can see that on the chart on the right hand side with the green profile. It's obviously not accumulating that same temperature increase because there are no losses to go back into the liquid. Now, another good point is it makes the pump more robust, and we're gonna take a look at that in a bit more detail here. So this was a test that we did to measure the temperature rise inside the back of the pump, comparing the zero loss shell to a metallic shell. But this also offers a good picture of the available power savings. So this is a really powerful point, not just because it illustrates the obvious cost savings, but we're seeing from all areas of industry the emphasis for a reduction in carbon emissions, and it's gaining more and more focus, and in some cases it's being driven from a government level. So this really puts it into perspective. So you can see on the top of the slide there, we take a GSP 2x1x13 and we fitted that with a zero loss shell, and this consumes 9 kilowatts less than the same pump with a metallic containment shell. So estimating a reduction in carbon footprint of 0.92 pounds of CO2 emissions per kilowatts an hour of saving difference. So what that means is for every kilowatt an hour that you save, you are removing 0.92 pounds of CO2 emissions. And so you can see with the power saving offered with the zero loss shell that that can make a massive difference. So going back to the previous slide about how the zero loss shell makes the pump more robust. So you can see there at the bottom point with a closed suction valve, the zero loss containment shell takes 3 minutes longer to increase by a temperature of 10 degrees compared to that of the metallic shell. So by eliminating all of this extra heat, it's giving you that little bit of extra time if you are to experience an upset condition or a dry run. Then with something as simple as a panel control monitor combined with a zero loss, this provides you with that critical window to stop the pump, making it far more resilient to damage. Just very quickly here, this is just a technical slide really, and highlighting the key design points of the zero loss shell. You can see some of the key ones there, that the temperature range going to minus 100 degrees or minus 148 F. All the way up to 120 degrees, and that's an important point to remember, because whilst the maximum design of the GSPV, as I said earlier, is 205 degrees, with the zero loss shell, that will then become limited to your 248 degrees F. Okay, so now moving on just to the vapor view. So this device, rather than being reactive, which is how most pump monitoring devices work, it's actually proactive, as it prevents the main reason for the pump failure to occur, which is dry running. Now, obviously, if you think about a power monitor there, if the pump starts to operate outside of its duty point, starts absorbing different power, it's starting to cavitate, or there's dry run, it's reacting there to a failure that's already occurred. So, as stated on the slide there, it will help measure and identify the cause of a potential failure rather than reacting once the process failure has occurred. And you'll see this, how it does this on the next slide. You'll have real-time monitoring with this device, but also onboard data recording. Now, the benefit of the data recording is that if you get a process change and an upset, you can send the data recording leading up to the shutdown to HMD, and we would be able to interpret this, and we'll be able to give you an indication of what changed in the process leading up to the shutdown. A really good site experience that we had with this, and a good example, is where the customer was using the vapor view on troublesome pumps, and they found that they were getting a blank signal before starting the pumps. And this indicated that the suction pressure was actually not sufficient and the liquid was vaporizing before startup. So this prevented a dry run start. So a really good, you can sort of see the real value that can bring to a process. So this device, it works using ultrasonic technology. So an ultrasonic signal, as you can see on the slide there, is passed through the containment shell wall, through the liquid inside, and is then bounced back from the surface shown within the pump. Okay, so you can see here in this expanded view, the vapor view sensor, it's in the outside, it's on the outside of the containment shell, so it's not in the pressure or the liquid area, it is on the outside pressed against the containment shell, and you can see how the signal is being passed through, it's being bounced off the bush holder here, so you can see that's where it is. And then it's then being sent back and received back at the sensor. And you can see in this image how that is a disrupted signal, because we're starting to see vapor appear in this hot channel here. And obviously this is where the liquid has passed over the inner magnet ring, where it's picking up all that heat. So the signal was processed by the onboard microprocessor, outputting the user with a 4 to 20 milliamp signal, and this is indicating the condition of the fluid. So you'll see this in more detail on the next slide. But it is important to highlight here that you'd only look to apply the vapor view on critical service, bad actors, or where suction and vapor pressure conditions are marginal on volatile liquids. For less critical service, you can still get a really good level of pump protection using a properly set power control monitors and temperature probes on the containment shell. And just to give you an idea of how sensitive the vapor view is and what the vapor view signal will look like, so you can see there at 0% gas, where you're looking at a 19 to 20 milliamp output, and then with just 1% gas, you are starting to see a change, so it is registering that. And then just at just 2.5% gas, I mean, if you look at that really, you can really see there that, and that's really starting to change the output there. And then 10% gas, you're seeing a massive change, and you're really seeing that output and the signal. So it is a highly sensitive response. So given the current standing in the oil and gas market, any upgrades that the customer is considering with seals, the above benefits, they highlight and present the perfect opportunity to make the migration over to sealless, to start making those savings. How easy is it to run and install? How reliable is it? How much does it cost? And how can you support it? So this is an opportunity to simplify installations, further reduce running costs, And it also provides an upgrade from an existing seal solution where space constraints might be prohibitive. So we also know that there are limited seal upgrade paths with some of the the vertical inline designs due to the bearing box. And I've said this before, API 682, it's not a specification that's getting any thinner. So moving through there's no cooling required. There's almost zero unplanned maintenance, because sealless pumps, as we know, they have no wear parts, therefore they have a longer mean time between failure. How much is downtime costing the customer? And this is a time when users are under pressure to reduce emissions, and the safety of their employees is paramount. And these benefits are the unique selling points of a sealless pump, and ultimately make the user's process for operation far easier. And there's no bearing box required for shaft alignment, so there's no potential for oil leaks. There's no EPA monitoring required, and as we've already touched on with the zero loss shell, this means an upgrade to the GSPV, the absorb power would be comparable to the customer's existing vertical inline seal pump. So we're coming to the end of the presentation now, but I also wanted to touch on the 801S, because we've seen an excellent response, with our upgrade approach, and we've generated a huge number of quotations, with almost every one of them being a seal to sealless upgrade. So with that in mind, I just wanted to draw your attention to the orders that we've received, as I think they tell a very good story about the type of applications where we will find the greatest success, and where a sealless pump can be an ideal solution, because every one of these orders has been unique in some way. So as you can see from on the screen there, they have all been the first 801S sealless pump for each of these customers. They've all been a seal to sealless upgrade, but I think that the most important detail is that they've all been bad actor problem seal pumps that have been causing headaches for the users. And what we've provided is an engineered solution, as you can see. So, except maybe JCI, which was unique because it was the first sealless that we've sold into a midstream. But looking at the top there, Energy Transfer, they were having problems with their seal at low temp. So we offered a minus 100 degrees C, so your minus 148 degrees F 801S with a zero loss shell. Angola LNG there, this was a step further, and we offered a minus 100 degree, minus 148 pump, but this one was rated for 100 bar. This had to have a metallic shell though, due to the high pressure requirement. P66 there at Ponca City, they were having trouble with their seals and their seal system, which kept failing. There were magnetic particles in this fluid though, but we managed to convince P66 that a sealless pump would be a great solution to this if we were confident that the solids weren't going to cause it an issue. And so we managed to convince them to carry out some proper solids analysis, and the results came back very positively. So as you can see there, to combat that concern, we included a magnetic filter. And finally, the Exxon Singapore, this order, this was actually replacing an 802. So in this case, the customer didn't even have the benefit of the interchangeable casing, but they saw the value in migrating over to a sealless. So they were happy to make the pipework modifications. And this was also the same from the Energy Transfer order, because I believe they replaced an 806. And that's this is the final slide. So yeah, just to wrap up, really, contact your ASM for any information that you require on this topic. And finally, the update and replacement GSPV brochure that is now available. So I think we'll be able to have all of these contained in the same place for download. So following on from this, if anything comes up, please feel free to get in touch with myself, Anna, as I say, or any of your ASMs, and we'll be able to follow up on that.